Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC, a series of lectures on optics, and especially on the section on diffraction, and the syllabus corresponding to this section is shown in this slide. Now we are going through the Corno's spiral, Fresnel's integrals, and the diffraction at a narrow wire. So in this lecture, we will start with the diffraction at a narrow wire, and then we will move on to the Corno's spiral. Hence, the contents are as follows: diffraction at a narrow wire, and then determination of thickness of a narrow wire, and also we will be discussing about Corno's spiral. We will start with the phenomenon of diffraction at a narrow wire. This is a very interesting problem, in the sense that I am going to talk about diffraction as well as interference. You know, diffraction and interference are sometimes synonymous, and it was told by the great Feynman that the two terms, there is no distinct difference is there between diffraction and interference. I will come to that later. Anyway, now we will talk about diffraction at a narrow wire. Now we have seen many cases when light is coming from your source, you place an aperture, a circular aperture. Then you place a rectangular aperture. You have an aperture like this, rectangular aperture, or you have a circular aperture, or you have got what are the other things you had? You had an opaque disc. You have a disc. Then now we pass on to a narrow wire. You got a source of light. This is my narrow wire, right? A narrow wire. So this narrow wire, light cannot pass through the wire. What will happen is the edges of the wire, the two edges, they will be illuminated, right? The edges obviously will be illuminated by the light coming from the source. So well, let us look at the diagram. You have S is a monochromatic source, a source of light. Light is coming from the point S, and you have a wire in the path of the light beam, and let us see what happens to the patterns that we will be getting on the screen. So now you have a slit illuminated by monochromatic light. AB is the diameter of the narrow wire, and MN is the screen. The length of the wire is parallel to the illuminated slit. So you got light here coming through a slit. Slit is nothing but an opening, right? Now you have the narrow wire. So light is coming through a slit, you have the narrow wire, right? In the path of the light beam, you put a narrow wire. The wire is obviously parallel to, not perpendicular, parallel to the slit, so that the wire will be illuminated. The two ends, the screen is also perpendicular to the plane of the paper, or the plane of the screen. Xy is the incident cylindrical wavefront. P is a point on the screen such that SOP is perpendicular to the screen. EF is the region of the geometrical shadow. Now let us consider a point P prime on the screen. Then you have O prime and other things as the pole. Then the intensity at P prime due to the wavefront above O prime is the same as at all points. Then the effect due to the wavefront will be negligible. The intensity at P prime will be a maximum or a minimum depending upon whether the number of off-period strips between O prime and A is odd or even. And the most important point I want to stress now is the following. Now, the wire that I am placing here in the path of the light beam, because of the fact that the edges are illuminated, the edges will act as coherent sources. We have seen the Young's double slit experiment, wherein light coming from two coherent sources give rise to interference pattern. You all know by now, to get a stable interference pattern, you have two coherent sources. You know what is meant by coherence. The two sources should be emitting light at the same wavelength, and the phase difference between them should be integral multiple of lambda, maybe lambda, 2 lambda and so on. Thereby the crusts will be meeting each other, or the troughs will be meeting each other. So you talk of the wavelength and the phase difference between the light coming from the two coherent sources A and B. So the points A and B, what are the points A and B? You have the wire. Let us assume this is the point A and this is the point B. So the two end points, you got a point A here, the light is coming, it is incident, the screen is here. The two end points A and B, they will act as two coherent sources. If you have got coherent sources, what will you get? Light coming from two coherent sources will interfere. Because these sources are coherent, you will be getting interference pattern. Remember, the point is, you are talking about diffraction of light because of a wire interposed in the path of the light beam or kept in the path of the light beam. You got a source there and I got a wire here. Light coming from the wire is obstructed. Therefore, you expect diffraction. But when I am talking about diffraction, or when I am trying to explain diffraction phenomenon, I come across the fact that the two endpoints are equally illuminated. So these two endpoints will act as two coherent sources. You have seen what you know about coherence, how do you get interference pattern and so on in the Young's double slit experiment. So because these 2 points are two coherent sources, you can expect an interference pattern and not a diffraction pattern. The point is, when you are talking about diffraction at a narrow wire, unlike the other cases, you get a pattern which is due to interference pattern. The interesting thing is, you get an interference pattern because of the phenomenon of diffraction. So the points A and B, which are the edges of the wire, are illuminated by the same source, which act as obviously as two coherent sources. The light coming from these two coherent sources will interfere, giving rise to interference bands or interference pattern. Okay, that is the important point. So the point that is important is you have the interference pattern that you are getting, and when you are talking about interference pattern, you can talk about what is called band width. Is that right? You have seen in the case of interference due to the double slit, you have a biprism, right? Or interference in the case of air wedge, or produced in the case of Newton strings. In all these cases, you have been talking about bandwidth. In the earlier lectures, I told you the differences between the interference bands and diffraction bands. In the case of interference bands only, you can talk of the band width. The distance between two successive bright bands or two successive dark bands is called the bandwidth. You all know what is the definition of bandwidth. Bandwidth is nothing but the distance between two successive bright bands or dark bands. All the bright bands will have the same intensity. In which case? In the case of interference bands, in the case of interference pattern. Whereas you go to diffraction pattern, as I told you in the last lecture, the intensity will not be uniform. The intensity will go up, come down, go up. You know, in the region where light is directly falling, instead of uniform intensity in the case of the diffraction, a straight edge, what you have seen is you don't get uniform intensity. On the other hand, you get the intensity maximum and then it comes down, then again maximum. The two maxima are not equal. So, the intensities of two successive diffraction bands, the intensity will not be equal. On the other hand, in the case of interference bands, the intensities will be equal and the width that separates two successive bands again will be equal. There is nothing like diffraction bandwidth. You don't have bandwidth in the case of diffraction bands, right. So, the important point to be understood is you can talk about bandwidth only in the case of interference bands. That is what I am having here. So, even though you are talking about diffraction caused by a narrow wire, the diffraction will give rise to an interference pattern, and when you are talking about interference pattern, you are allowed, you have got legitimate right to talk about the bandwidth. So, beta, the bandwidth will be capital D by small d into lambda. Where from do you get the expression? This expression we are borrowing from what we have studied in the case of Young's double slit experiment. What is small d? Small d is in the double slit experiment, or you have two coherent sources. Small d is the distance that separates them, two coherent sources. What is capital D? The distance that separates the coherent sources, and the screen is capital D, right. So, beta is the bandwidth, you know, beta is the bandwidth. The fringe width or bandwidth beta is given by beta is equal to capital D by small d into lambda, where capital D is the distance between the two coherent sources or the two virtual sources produced by a single real source. So, the two virtual sources are here, the screen is here, the distance between the screen and the virtual sources is capital D. Small d is the distance between the two virtual sources, that is your small d. Lambda is the wavelength of the monochromatic source. So, I write now d is the distance between the wire and the screen, lambda is the wavelength of the light used, and d is the distance between the two coherent sources. So, in this case d will be equal to 2r, because d is what? If the diameter of the wire is d, or if the radius of the wire, d will be equal to 2r, right, the diameter of the wire. Therefore, you can write beta will be d into capital lambda by small d will be 2r, right, this is what I have written here. So, obviously, r will be d lambda by 2 beta, or lambda will be 2r into beta by d. These things are simple things. So, here beta is the fringe width corresponding to the distance between any two consecutive maxima. Now, having talked about the pattern that we are getting here, we will have a break at this point and we will come back with the rest after the break. Welcome back after the lecture. We are seeing the problem of diffraction of light at a narrow wire. As I told you, when you have a narrow wire in the path of the light beam, the edges of the wire are equally illuminated, and these two edges will hereafter be thought as if they are the two coherent sources of light, as you had in the case of Young's double slit experiment. So, when light is coming from two coherent sources, they will interfere and give rise to interference pattern. When you are talking about interference pattern, remember you are talking about interference pattern when you are talking about diffraction, and when once you talk of interference pattern, you can talk about the bandwidth, and the bandwidth that I am having here beta as d by 2r into lambda. This 2r is nothing but d, that is the diameter of the wire, because the diameter of the wire is nothing but that is the distance that separates the two sources, because this acts like a source. This edge also acts like a source. There are two coherent sources, and in the case of the Young's double slit experiment, you had the familiar expression beta, the bandwidth being given as capital D into lambda by small d. What is small d? Small d is the distance which separates the two coherent sources. So, these two act like coherent sources, that is the diameter, that is the distance separating the two coherent sources, nothing but the diameter of the wire. The diameter of the wire is nothing but 2 times r, that is what I am having here, 2r in the denominator. Hence, the radius of the wire which we want to calculate using the experiment that we are performing now, that is the diffraction of light at a narrow wire, can be used to study the or determine or evaluate the radius of the wire, because this diffraction gives rise to interference bands, and by measuring the bandwidth beta, right, if you measure the bandwidth beta, then knowing lambda, you know the beta is known, lambda is known, d, what is d? That is the distance separating the wire in our case, because the coherent sources are here, the screen is here. So, the distance separating the coherent sources and the wire is capital D. Now, because you know capital D, the place where the wire is kept and the screen, capital D is known. The wavelength of the monochromatic source, the mercury vapor light or the mercury vapor lamp, 5893 angstrom unit is known. Beta is a thing that can be measured at ease using a microscope or a telescope. So, you determine all these things, that gives them the radius of the wire, or in other words, if you know the radius of the wire, which can be determined using a screw gauge. The more important thing, the diameter or the radius of the wire can be easily determined, but cannot be determined very easily is the wavelength of the monochromatic source. If you want to calculate the wavelength of the monochromatic source, you can use the expression as given, the equation 3, lambda, the wavelength of the monochromatic source will be 2r into beta by capital D. Here beta is the fringe width, corresponds to the distance between any two successive bright bands or consecutive maxima. From the equations 2 and 3, knowing the values of lambda 2 and 3, you use either 2 or 3. Using equation 2, you can determine the radius of the wire, or using equation 3, you can determine the wavelength of the monochromatic source. So, this is how the pattern will look, the diffraction pattern will look. The point is, important point is, the interference bands will be looking like this. You know, the wire, the edges of the wire, they will act as two coherent sources. When light is coming from two coherent sources, they will interfere, and the interference may be constructive or destructive. Wherever there is constructive interference, you get a bright band, then dark region, dark, bright, and so on, as you have seen in very many cases in the Newton's experiment or Fresnel's biprism or the air wedge. You get alternate bright, dark regions. Therefore, the same thing I am showing here. So, you get the interference band, And this is a very important problem, that is namely your diffraction at a narrow wire is an important problem. The intensity distribution due to a narrow wire is shown in figure E. The center of the geometrical shadow is bright, you have the geometrical shadow. On the other hand, if the wire is very thick, the interference bands cannot be noticed. The phenomenon of interference that you are talking about will appear only for a narrow wire and not a thick wire. The wire is too thick, something like the straight edge, then you won't be getting the interference pattern at all. Okay. Even this interference pattern, in the case of even double slit experiment, the two sources should be very near to each other. Therefore, if you want to have the stable interference pattern, one of the conditions is the two sources from which light is coming should be very near to each other. There cannot be, the two sources cannot be far off. They are far off, you won't be getting a stable pattern, interference pattern. So, beta equal to capital D into lambda by 2, or where beta is the fringe width. This can be used to determine the diameter of the wire. As the diameter of the wire increases, the fringe width decreases, and if the wire is sufficiently thick, the width of the interference fringes decreases considerably and they cannot be distinguished. So, the pattern will collapse. So, thick wire you don't have the thick wire, the geometrical shadow, you won't be having the so called the interference pattern. The intensity falls off rapidly in the geometrical, this is the geometrical shadow, right. The diffraction pattern in the illuminated portion will be similar to that of a thin wire. Colored fringes will be observed with white light. Now, pass on to what we call as Corno's spiral. And nowadays, with the advent of high speed computers, the Corno's spiral evaluation of the intensity distribution using Corno's spiral or using Fresnel's integrals, about which I will be talking in the next lecture, not so important. As high speed computers, we can calculate some of the quantities at a faster pace. But anyway, to find the effect of the diffraction pattern or to find the intensity at a given point due to an incident wavefront, Fresnel's method consists of dividing the wavefront into half period strips or half period zones. The path difference between the secondary waves from two corresponding points of neighboring zones is lambda by 2 or t by 2. They are called half period zones because the time difference is t by 2, or path difference will be lambda by 2, or a phase difference will be pi. So, S is a point source of light, which I will show in a moment. Xy is a spherical wavefront incident with reference to the point O P. O is the pole of the wavefront. Let A and B be the distances of the point S, that is the point S here, right. Source here, the P, the point where I want to evaluate the intensity. What we have been doing so far, we had a light source, we had a straight edge or an aperture or a narrow wire from the point S, from where light source is coming. What is the intensity they obtained on the screen, that is what we have been trying to obtain. Now, Corno's spiral is a different approach by which you want to find the intensity at a given point. So, I am showing the xy is the wavefront that you have here, the incident spherical wavefront, and A and B are the distances which are shown here. A is the distance between the spherical wavefront and the source, whereas B is the distance that separates the pole of the wavefront and the point P, the point where the intensity is to be determined. I think you should know the things like you got a source here, the point P is here where the intensity is to be determined. the wavefront is here. Okay, and these you have to draw them perpendiculars from here to here and from here to here. From the kind of mathematics and the final expression I am going to get, they all will make use of the A, B and these distances. With P as center, where is P? The P as center, right? And radius B, let us draw a sphere touching the incident wavefront at O. With P as center, with B as the radius, draw a circle. There is a dotted circle, which will be touching the pole at this point, right? The wavefront is being touched at this point. Okay. The path difference between the waves traveling in the directions SAP and SOP is given by D. Now you have to know SAP and SOP. The paths traveled by the light beams SAP and SOP. What is SAP? SAP is this distance. SOP is the direct distance, right? So so what is the thing? You have to this particular difference will come. So SAP, what is SAP? It goes here and comes here. SOP is the straight line connecting S and P. Okay, so the path difference will be D is equal to SA plus AP minus SOP. That will be SA plus AP minus SO plus OP. Where is SO? SO is here plus OP is here. Okay, so SO and OP are here. SO is nothing but A, right? SO is nothing but A, and OP is B. So your SA is nothing but A, and AP will be AB plus B. So that will be so much. S is a point source of light. XY is the incident spherical wavefront. This is what we have drawn now. A and B are the distances separating the point S and P. So the same thing is for the sake of continuity I am showing this. Let us now calculate the path difference between the two beams SAP and SOP. The mathematical derivation that we have to ultimately get, we have to see in the next lecture. Now let me now pass on to the summary of what we have seen so far. The summary goes as follows. In the case of a thin wire placed in the path of light beam, the two edges act as two coherent sources which give rise to interference bands. The diameter of the wire can be determined by measuring the bandwidth of the interference bands. Cornu spiral can be used for any diffraction problem. The intensity at any point can be calculated using this method. The questions are: explain the diffraction effects when light is intercepted by a thin wire. Do you get diffraction bands or interference bands in the above? Justify your answer. How do you determine the diameter of a thin wire? Last question: what do you understand by Cornu spiral? With this we come to the end of this lecture. We will discuss in detail Cornu spiral and Fresnel's integrals, which comes in this connection in the lecture to come. Thank you.